Hello to everyone. Today I will be discussing about the electronic spectra, Frank-Condon principle. Let me discuss the silent feature of the molecular electronic spectra. The most complex molecular spectra is a electronic spectra and appearing in a visible and ultraviolet regions and involving in the change in all the three electronic, vibrational and rotational energies of a molecule. And such spectra are studies both in the emission and the absorption, and band shows that the fine structure, usually more complicated as what we have done in the vibrational rotational bands. The tendency of head formation is very strong in the electronic spectra, and the bands may degrade towards the red or towards the violet. That is the lower wave number side or the higher wave number side. All molecules exhibits the electronic spectra. Homonuclear such as H2N2O2 which have neither a rotational or the vibrational spectra because they do not have a permanent dipole moment. Electronic spectra, because the instantaneous dipole moment changes during the redistribution of the electron changes, which consisting the electronic transitions for homonuclear diatomic molecule. Now, this is the simple how this electronic spectra. Now, how the formation of the electronic spectra. When one of the atom forming a diatomic molecule is electronically excited, that is, its valence electron is pushed into a orbital further, the higher energy states said to be an electronically excited state. The various possible electron arrangement for a given molecule form a pattern of molecules allowed electronic states of the molecule. For each of the electronic states, there is a different electronic states. There is a different dependence of the molecules energy of a internuclear separation. Means that once we have a different electronic states, it means that we will have a different potential energies for the different energies level, electronic levels. That each of the electronic state of a molecule has a different potential energy curve characteristics. So by a minimum provided at the state where its internuclear distance is minimum, that is the equilibrium state. And this dissociation limit is dE. So we will be defining that dissociation energy dE. So again, the single primes are defining for the higher energy levels. Either is the rotational one or the vibrational one or the electronic one. However, this double prime are the lower energy levels corresponding to electronic one, vibrational one and the rotational one. So these diagram is two typical potentials for a diatomic molecule are shown in the figure. The lower one shown that representing the ground state of a molecule, upper is electronically excited state. So, but if you look at, these curves are differing in the shape for the excited state and the ground state. The asymptote of the upper curve is higher than that of the lower by the electronic energy of the excitation. Asymptote of this curve is higher than as compared to this by this excitation. Excitation means asymptotes means that the tangent where they are matching, means once I will put at this tangent and where they are crossing, and the tangent I will draw where they are crossing. These are the asymptotics. Asymptote of this upper curve is higher than at the excitation energy of this electronic level. And more interestingly, the position, the shape as minimum asymptotes, and in addition, The electronic upper and the lower states are defined by this T of Te prime and Te double prime for this excited state and for the lower state, that is the electronic states in the centimeter inverse. And the difference between these levels we defined with a wave number, that is energy nu of E electronic. So this is the difference between two minimas of this ground state and the excited state. And more interestingly, as I said that their potential curves are different. If you look at these electrons are loosely bound and they will be separated by the higher distance. So the minimum equilibrium for this one, it R double prime, it means that this R prime will be slightly higher. So these R prime and R double prime are not coinciding. And be careful, these are not coinciding each other. So this distance is a different as compared to this R prime for the excited state. When a transition of a molecule from one electron state to the other states take place, emitted or the absorption follows the visible and ultraviolet. These radiations are falling in the ultraviolet or the visible region, because of the energy separation between these electronic states are from the 1 to 10 electron volt. The energy difference for the electronic states are in the range of 1 to 10 electron volt. So the electronic transitions accompanied by the number of transitions involving the vibrational level of the upper and the vibrational level of the lower electronic state. If you remember that once we did that the vibrational rotator, in that case you have a transitions between this rotational state of the upper vibrational state and the rotational state of the lower vibrational state. In the same fashion that there will be transitions taking place in between this different vibrational level of high energy state to the different vibrational level of the lower energy state, electronic state, as well as the different rotational state of the higher electronic state to the any of this higher electronic state to the lower energy state, or vice versa. So electronic state, each such vibrational transitions in turn consisting by the number of transitions involving in the rotational level of the upper and the rotational level of the lower level of the states. So such such transition has been shown in the figure, that the rotational level of this vibrational level of 1 to the rotational transition to the vibrational level to V nu double prime 0. So this is the one of the transition has been shown in this figure. These rotation transitions give rise to the group of fine lines which constitutes a band. So if these transition lines are providing you a band. That is, a band arises from a particular vibrational transition and a band arises. So if the band is arising from a particular vibrational level, then this is called the band. And if the bands arising from all the vibrational transition, if these bands are arising from all the vibrational levels, these are called the band system. So within this vibrational one, you have a transitions. If all the transition taking place for all the vibrational levels, within these vibrational levels, the transition taking from the different rotational states, and then this is called the band system. So it means that a single electronic transition in a molecule gives rise to a band system. The bands of a system which corresponds to the same upper vibrational level but different lower vibrational level are said to be the V nu double prime progression. If these bands are forming from a single vibration level to the different vibration level of the lower energy state, and then this is called the new double prime progression. And if the transition are taking place for all the vibration level of this upper state from a single vibration level from this lower state, and these are called this new prime progression. New prime progression. So this is the basics of all the basics of this electronic spectra. And now if you look at this higher energy state potential is more shallower, the depth is less, more shallower, and much wider as compared to this one, as this your equilibrium distance for these atoms will be the higher. And the asymptote of this curve is higher than as compared to this excitation energy. And this transition, this minimum energy of this potential to the minimum energy, this difference is defined by this new electronic. And if this new transition taking place is new prime, this first vibrational level to this first vibration, that is the ground state, this minimum vibrational level, then this is defined by nu of 0, 0. This is the basics about this electronic spectra, how these potential energies can be plotted with respect to the intermolecular distances, and how this molecular spectra, this molecular energies in the y-axis. And this is the whole about this electronic spectra. And this now even at a diatomic molecule, homonuclear diatomic molecules, which are doesn't provide any rotational and vibration due to the due to the dipole moment. The dipole moment is 0 in that case, but in the redistribution of the energy states, they have an instant change in their dipole moment. That is why you have electronic transitions. So this is all about this electronic spectra. Then now we'll discuss the vibrational structure of an electronic band system. Vibrational structure of band system. So in another lecture, I will be discussing this. Thank you.